So now the next speaker is Gus, who's going to tell us about the the cluster approach to character varieties.
Okay, well, thanks for having me. As Ken mentioned, I'd like to use my lecture to kind of give an overview or introduction to a way of approaching thinking about character varieties and sort of an area of quantum topology you might call quantum pipeline theory, kind of from the perspective of cluster varieties. A lot of the sort of flavor of my talk is going to be somewhat more kind of combinatorial maybe than some of the other discussions we've seen so far this week. But sort of as a counterpoint and as an advertisement for Dr. Shapiro's talk on Thursday, he'll explain a nice kind of categorical way to think about some of the things I say using the tools of parametrizing. Okay. So what's the kind of setup that we're going to be thinking about? Well, we're interested in character varieties for surfaces. So S for me is going to be an oriented surface. We're going to allow surfaces with boundary. Allow the boundary of S to be non-empty. And we're also going to allow ourselves to consider a collection of marked points, a collection of special points living on the boundary of the surface. As I said, x1 up to xm of marked points. So the other sort of piece of input we're going to need is to fix the choice of G, a simple complex Lie group, and most of the results I'm going to mention during the talk are going to be in the case of when G is the projective general linear group, and feel free to fix that as your example in your head as we go along. Okay, so the basic kind of objective study, the basic thing we're interested in is a G local system on our surface. So let's quickly review what we mean by that. So a G local system on S is just a group map, group homomorphism from the fundamental group of our surface to our group. Okay, so the group G, another name, rho. So what do you know about fundamental groups of surfaces? Well, at least if our surface is closed, then the fundamental group has two G generators where G is a genus of the surface, and there's one relation which is the product of its commutators is equal to the identity. Okay, so to give the fundamental group is to give two G elements of G such that the product of commutators is equal to 1. In particular, the set of all of these G local systems, obviously I1 this to G is some affine variety.
So S is compact?
No. For most of what I want to say, I want to think about surfaces with boundary. Then you simply won't have.
But no infinite genus.
No infinite genus.
Yes,
That's
so with boundary but compact.
Yeah, with boundary but compact. Okay. Right. So this set of all homomorphisms from fundamental group to G is some affine variety. Okay. But what we're sort of really interested in is these key local systems up to isomorphism. What do we mean by isomorphism? Well, the group G acts on the set of these local systems by conjugation on the target. One of these homomorphisms rho, you can conjugate the image by any element of G, and get some action of G on this affine variety. And we're really interested in studying these local systems up to the notion of equivalence. All right, so classically, what was done at this point was something, was sort of the following thing. Which was to form a new affine variety called the classical character variety. Let's call this fellow Sh, depending on the P and the surface S. Basically, so some affine variety, so it's spectrum of some commutative ring, and that commutative ring is just the ring we get by taking functions on this space of all homomorphisms, and then taking G invariants, functions. Okay. Right. So this is what people generally mean by the classical character variety. It has some sort of defects, which is the notion of equivalence that this classical character variety describes. In other words, when the two local systems describe the same point in this character variety is sort of rather strong. It's really saying that they're equivalent when the closures of their orbits are the same. This is some very kind of overly strong notion of equivalence classes with these points of this character variety parameterizes. And it's also sort of not a particularly nice variety either. Right? So I'm not going to talk about these classical varieties at all really in the talk, but what I'm going to focus on is some sort of way to kind of tame them a little bit. This idea, which I'm not sure if it was originated by these two people, but was certainly very well studied and exploited by Fock and Goncharov. So our problems with this character variety basically stem from the fact that the action of G on this set of homomorphisms was not free, had stable headers. So this idea of Fock and Goncharov is a sort of general instance of this general idea of when you have something which fails drastically to be free, let's introduce some extra data in order to kind of frame the situation and make our action more free. So the idea is to study what's called framed G local systems on the surface. Okay, so I have to explain what this additional framing data consists of. The framing data is phrased in the following way. So let's pick B inside of our simple group, a Borel subalgebra, a subgroup, I should say. Okay, so we now have a main example of PGLN. Feel free to think of the invertible upper triangular matrices in there. Space of cosets, the flag variety. Okay, so given a local system, which we like to think of as a principal G bundle with a parallel transport, we can form the associated flag bundle. The sort of twisted product quotient by the action of G of our principal bundle And then what is a framing? Oh yeah, is it visible if I write here, or I should switch to the next one? Next. Okay. Right. So framing is a flat section of let's give this thing a name. Let's call this FL of this associated flag bundle, restricted to the set I get by taking the boundary of my surface and deleting out from it a collection of special points. Okay. So this is the.
So what was P again?
Yeah, P is this associated flag bundle. So I take. Sorry, P itself. Yeah. So we have our local system, which is a homomorphism from pi1 of S to G, and we can construct from that a principal G bundle. If you like, explicitly, you can take the universal cover of S crossed with G, and then just mod out again this sort of same construction by the action of pi1. Okay. Any other questions on that? All right, so let me first define this framed character variety. Let's call this fellow chi GS. So this thing is going to be a moduli of framed G local systems on our syntax. Okay, so let me unpack for you what this framing data consists of in a few simple examples. All right, so first example, let's consider our surface just to be a disk together with a collection of 3 special points on this boundary.
And what is flat mean again?
Right, yes, so let me unpack what flat means in the example. It will be more clear. Right? In the next example, it will be more clear. So in this example, right, our underlying surface is contractible. So there's no data at all to the underlying representation of pi1. The only data is that associated with framing. What this flat section means is essentially that we're need to associate a section of the flag bundle over each component of the puncture boundary. Each component of the puncture boundary in this case is an interval, which is again contractible. So we're just associating a flag to each of the 3 components of this puncture boundary. Okay, so in this case here. IGS is just triples of flags, points in a G mod phi, modulo the diagonal action of P changing basis in the vector space in which these flags are. Okay, let's do another example which will clarify the meaning of this section. So now consider the case where our surface has some non-trivial fundamental group. So let's take an annulus. Again, let's put 2 special points on one of its boundary components. Right? So now our puncture boundary is a little bit more interesting, right? We have 2 intervals, I1, I2, and a circle. So now, what does my framing data consist of? Well, again, on these contractible pieces, I just have to give you the data of a flag. So say a flag F minus on this left boundary, a flag F plus on the right. Now, on the circle, something more interesting happens, right? So, in order for me to have a well-defined flat section trivialization, I need that when I want to stick a flag f0, some point on this circle, then I apply my monodromy coming from the non-trivial element of the fundamental group, I should come back to f0. Okay, so we have this condition that G is the monodromy around the loop, that G should preserve this flag to the circle component of the function band. So putting it all together, our modular plane space now consists of, well, now we have to describe the underlying local system. So a hom from Z into G is just an element, this element of G that we drew in green. We then had our three flags, F minus, F0, and plus. We now have this condition that G ought to preserve the flag living on the circle, and to avoid messing up my picture, we'll put a question like that. Where now G acts on this group element G by conjugation. Change the basis, this point here if you like, and also by changing simultaneous change of basis.
Sorry, can you say again what P is?
Right. So P is the principal G bundle associated to this G local system. So you can think of.
Do you require at least one mark point on each boundary?
Yeah. So, well, at the, I mean, you can certainly define this thing for basically anything. In order for the next thing I say to be true, we are going to want, basically like an Euler characteristic description on the set. Yeah. So in the case when we just have this, we're going to require 3 mark points. But you see when we have this annuals we can get away with.
So here you did not have a point on the interior boundary component.
You certainly don't have to have a point on every component.
Not on every component, but it's a condition on the overall Euler characteristic. Exactly, it's precisely that. We need to have enough kind of, like each one of these marked points is giving us sort of a new component of the function boundary, giving us a little bit more framing data, making that a little bit more frame. Alright. So what's the point of introducing these framed these framed guys? So maybe I'll delete this stuff on the left. So we mentioned that the classical character variety who I just erased have slide. Oh no, I didn't. This is okay. So this classical character variety was not a particularly nice variety in general. On the other hand, what Fock and Goncharov showed is that these decorated moduli spaces of decorated local systems are actually nice rational varieties. And they come with a special collection of open embeddings of tori. So a sort of split algebraic tori. So you start with a dimension of the moduli space. Alright, so what I want to do is explain how to construct these special toric coordinates, if you like. So let me begin by explaining how the story works. Firstly, in the simplest case, when our group P is just PGO2. Just a simple group of rank 1. Okay.
Sorry,
so
just a handwriting question.
Yeah.
Your superscript on this C cross for these embeddings.
Oh,
what,
yeah,
what is
yeah.
that?
Just D. Just my name for the dimension of the model. Yeah, so these are open embeddings of this one.
The classical characterizing the quotients of
That's so there's a projection from the strain guide to the classical guide. We just forget all the frame there. Okay, so let me explain how these embeddings are constructed in the case of PVL2. All right, so so these embeddings are labeled by some combinatorial data. And that combinatorial data is what's called an ideal triangulation of the Mark surface. Okay? So in order to say what that means, let's imagine that we take all of these circle components of our puncture boundary, we imagine shrinking them down to just punctures on the surface. Right? So we shrink S1 components of the puncture boundary. Down to punctures. Okay, and then let's agree that an ideal triangulation of S is just a triangulation whose vertices are at these punctures or these special points on the boundary. Okay, so let's look back to these little examples we drew a little earlier. So in the first one, the situation is pretty silly because we only have 3 vertices, so there's only one possible triangulation we can only one triangulation of these pieces of boundary, these 3 intervals in the puncture boundary. On the other hand, let's see what we have in the second example. So now I'm going to do my procedure of shrinking down this circle component of the boundary to a puncture. And now we have triangulations, for instance, we have one like this. An example, an ideal triangulation of this if you like puncture disk with 2 points on it.
So do you only shrink those boundaries without any
Without any mark points, yeah, that's right.
There are other triangulations of that.
There are, yes. So that's a really good point. Just to illustrate the sense in which we mean triangulation, there are also triangulations of this thing which are what you might call sort of self-folded, where 2 edges of the triangle have been glued to each other. You'll erase this and you just draw next to here another thing which is valid in this world of ideal triangulations. So we can have kind of a degenerate triangle where we've glued 2 of its edges together. So now we have one triangle, this guy in the middle, and this other triangle we have this edge. This is also a valid triangulation.
So you don't have to use all of the points. You don't use the one at the top.
Oh, no, the one at the top, let me draw yes. So there's one triangle, which is like,
The whole thing has to do with it.
yeah. So there's like this triangle, and then this funny guy here folded up in the middle. All right. Right. So in the case that our group is
In the previous example, somebody drew like a triangle.
Yeah.
The previous one. So, like in the middle was triangle.
Yeah, that
Then there were like 2.
yeah, I shouldn't have drawn that.
So, the triangulation.
Yeah, the triangulation is this, and the triangle is everything in the middle. It's the whole thing. Okay, so remember our goal at the moment is to construct this special collection of embeddings from these tori into the modular space. So when you use PGL2, then these special collections of embeddings are enumerated by ideal triangulation. So for each ideal triangulation, delta, we're going to construct embedding I sub delta from C star to the D into our modular space. All right, so now let me tell you what D is, what the dimension is, right? So maybe let me not go too far below it's visible. This board here is fine, right? Like, or, okay, yeah. So, all right. So, so the coordinate directions, these toric coordinates, of which we have D, are in correspondence with edges of the triangulation. Okay, so here, take this picture at the bottom, we have 4 toric coordinates. We have 1 and x1 sitting on this edge, another x2 here, x3 here, and x4 over here. Okay, so the number of coordinates is equal to the number of edges in the triangulation. Now let me explain how, knowing the value of these numbers attached to the edges in our triangulation, we can actually construct a framed local system. And the way that's going to go is illustrated in these 2 pictures on these second to last column of 4. Let me go over it. Okay, so constructing a local system from the coordinates, these numbers on the edges, goes in the following way. Okay, so we're trying to build this local system, like this principal key bundle with a parallel transport. And what I'm going to tell you how to do is how, knowing these values of these coordinate functions, you can build the elements of P, which are the parallel transport matrices. All right. So the strategy for doing so is going to be the following. Right. So what we're going to do is we're going to take our surface. So imagine here in these pictures we have some piece of our surface, piece of our triangulated surface, and we're going to retract our surface S onto this kind of ribbon, which is a sort of multicolored ribbon that I've drawn, which is dual, whose sort of core is the dual graph of the triangulation. Dual to the triangulation. Okay. So if we sort of put in dual graph of the triangulation, looks a little like rendering in white, and we sort of thickened it up into this multicolored ribbon. All right. So now what I am going to do is I'm going to cut the ribbon up into some sort of tiles of 2 shapes, some squares and hexagons. And the way I do this is that for each triangle, in other words, for each vertex of the dual graph, I draw a little hexagon. And the so we have this hexagon, which consists of 3 of these sides I've drawn in red and 3 in blue. Okay, so we have red and blue edges, and then we have squares, or these rectangles, which are these guys that I've drawn in sharing these green and red represent these rectangles which sort of are crossing the edges of the triangulation. Okay, so each one of these green rectangles with green sides is cut by the one edge of this original triangulation. Okay, and now let's also orient all of these little colored segments so that we're always going, let's say, clockwise when we're running around our points of the dual graph. Okay, so now what I'm going to tell you is how to associate a matrix in PGL2 to each one of these kinds of segments. So to these green, red, and blue segments. Okay, so the way I'm going to do it is as follows. So to the blue segment, I'm going to associate the matrix in PGL2. This upper triangular unipotent guy, let's call him name E. Alright, to the red segment, I'm going to associate this representative of the longest element of the Weil group of PGL2, signed permutation matrix, I'm going to call him W. And to the green segment, crossing the edge of the triangulation, which is labeled by the toric coordinate x sub I. So remember, the edges of the triangulation are corresponding to the coordinate directions on my torus. I'm going to associate an element of the torus, this guy xi, stick my coordinate, toric coordinate in there. All right, and then you can check that if you go around one of the hexagons or one of the squares that we've drawn here, the product of all of these matrices I've assigned is just going to be the identity. Okay, the products around faces okay, so we get a actually consistent parallel transform. All right, so
does it matter which the orientation of the green how it crosses the white?
Yeah, it does. Yeah, and the way we orient it is to be consistent with our orientation of that hexagon. So let me complete the orientation of the green guys, right? So this guy's going to be going up, this guy's down, this guy in.
Oh, is the matrix XI inverse on the reverse orientation?
Yeah, that's right. Yeah, and so you invert. Yes. So these are, let me say, oriented segments. We assign these matrices, and when you traverse it in the wrong direction, you just multiply them. Okay.
So wait, this last thing, like check the products of
yeah.
faces. Is that, can we go around the face?
Yeah, right. So going around the face means if you say start at this point here, you multiply by W naught, xi, W naught, and the inverse of this.
Okay, so by face you mean these ribbon faces?
Yeah, the ribbon faces, that's right. Yeah. So we can really contract and pull that down onto the original ribbon. Okay.
And that's enough to construct the whole thing because the surface retracts.
Exactly, because this retracts and it's back onto the midline of this ribbon.
So that constructs the local system, but you also had these flags.
Exactly, that's right. So the data of the flag comes from the fact that this matrix E is upper triangular, so it preserves the standard Borel. So what we're really saying is we sort of pick a parallel transpose, like we take the standard flag here, and then we transport that standard flag using the parallel transport. So the interesting situation, right, is in the case where we have a puncture, and now the point is if you think about what you matrices you have to multiply when you go around this puncture, you're going to be multiplying together a bunch of upper triangular matrices. So that monodromy preserves the standard flag.
So if I go to higher rank, is that a regular nilpotent, or what do you put in?
No. Yes. So I'll explain in just a second how it goes for higher rank.
You can't tell blue from green from here. So
I'm sorry. Yeah.
Green crosses a white line, blue does not.
That's right. Yeah. Yes. So green crosses edges of the original triangulation. Yeah, and the blue guys are edges of this hexagon surrounding vertices. Yes, sir.
So, let's say that I don't have a triangulation.
Yeah.
But, I have some looser thing
Uh-huh.
that has two refinements called triangulation.
Uh-huh.
Is that compatibility supposed to be how I glue these C star ends together?
So, yes. So let me explain. Yeah, I'll come to that right now. Okay, so how am I doing time-wise? What are the 20 minutes? So I think I'm going to subject you guys to a little bit of sort of type 2 and to illustrate what happens with the gluing. All right, so let's do some sort of simple example of computing one of these. Right, so given one of these triangulations, whenever I have two triangles which fit together into a quadrilateral, there's a sort of local operation I can do on this triangulation, which is to flip the diagonal edge. Okay, so here you see I have these two triangles with this diagonal pointing sort of northeast, and here I flip it to get this picture. So these guys are related to flip of the diagonal. Okay, and now what I want to do is to compute the parallel transport for this local system from the left vertical edge to the right vertical edge in these two different toric coordinate systems corresponding to these triangulations related by a flip. Okay, so how does it work? Well, let me call this thing number 1 and this thing number 2. So then so in number 1, what do we have to do? Well, again, let's also let's have to pick which side of the ribbon graph we start on. So let's go from top of the left to top of the right. So here, what we can do is we can first do h of x1. You do this green edge crossing the variable on the left. Then we do w, the inverse of e, because we're going backwards, and w again. Then h of the variable lying on the middle diagonal, and then we need to do e, finally an h of x. Right? So this first.
H of something is your xi 0, 0, 1.
Yeah, that's right. Yeah. Oh, yes, right. Sure. Thanks. So let's call this fellow h of xi. Yeah. So you see we sort of factored out parallel transport, sort of Gauss factorized it. This w, e inverse w, is just this matrix 1, 1, 0. It's a Cartan involution. So we factored it as sort of lower triangular times upper triangular, whereas in no, right. Let's just say E inverse gives you the -1, and then you do this way you do the sign.
And could you I was like, could you redo the order that you were tracing it when x1w, e inverse w, like just
Of course, yeah.
I missed it.
Here, shaded. So which form was I doing? I guess I was doing this one, right? So we went like this,
We crossed x1, I see that.
and then we did
Ah,
this. So this little bucket thing is my w, e inverse w. Then I did another h, then another is regular e, and then
and that was just a totally arbitrary path through there?
you could have picked any other one, you would have got the same matrix in PCO. Because of the fact that these products are on the basis of okay. And the second triangulation, this corresponds to the opposite Gauss factorization, right? So here we can have coordinates x1 prime, x2 prime, x3 prime. And now what we're going to do is take x1 prime, we come along here. Now we can do an honest e, we're traveling in the right direction. And an h of x2 prime. And now we're sort of in trouble because we have to do a w, e inverse w. That thing is what we call f. And then finally we're back up here and we can do our last h of x3 prime. Okay. So this is the opposite Gauss factorization, in fact it is lower times upper. Okay, and now the sort of trivial observation is that the coordinates x and x prime are related in the following way. So if you multiply all these matrices out and solve for the primes in terms of the unprimes, so you see that x1 prime has to be x1, x2 over 1 plus x2. The second, x2 prime has to be 1 over x2. The third has to be x1, x2, x3 over 1 plus x2. Okay, and here it's important you think of the matrices as being in PGL2 rather than PGL2. Where?
And in your labeling, was it the prime versus the non-prime? Like I'm kind of surprised it's like on the top, on 1, you have x5 on the top and x4 on the bottom. But in 2 you have x4 prime on the top.
Ah,
and x5
sorry,
on the
yeah.
bottom.
Sorry, yeah.
Ah.
Yeah, I mean, I guess you can call it how you like that. Yeah, it's very
I mean, is it?
Yeah. Okay. And to write the unprimed in terms of primes, it's kind of similar looking now. So it's 1 prime 1 plus x2 prime, x2 1 over x2 prime, and x3 prime 1 plus x2 prime. Alright, so the particular form of these change of coordinates is nice, but it's not particularly important here to worry about. What's really important is that the this transition function you might call subtraction free by rational isomorphisms. Right, there are elements of the components of them are elements of the fraction field that you can represent as a ratio of a polynomial for whose coefficients are positive divided by another polynomial.
And so you're getting something that is for each such path? Because like, for instance, you don't see x4 and x5 because you didn't pick a path.
Right, yeah. So to see what happened to x4 and x5, you'd have to look at what happened to this.
And then that would tell you what to do.
That's right. You could also deduce it by turning your head 90 degrees and looking at this and reversing the picture back to sort of the symmetry. Agreed. All right. So the key thing about these transition functions is that they're subtraction free, right? So if I start with a point of the moduli space where my unprimed coordinates are positive, then my prime coordinates are going to be positive as well. Vice versa, if my prime coordinates are positive, so will be my unprimed coordinates. Okay? So there's a well-defined chart-independent set of positive points. We call it, say, x key s points in varieties. You can take points in any sort of semi-zero, right? Of positive in this case, going to use it with these this set of the positive points recovers the classical type Mueller component in the PSL2R character.
How far away from central Wilson now?
Quite far. Yeah, these coordinates are, they're kind of two special sets of coordinates on these technical spaces, the the length twist coordinates and also the shear coordinates. And these are like the shear coordinates. I'll talk maybe if I get time about the function Wilson, but they're also really, really important. Okay. So that's the complete story for groups of rank 1. Let me now sketch how it is promoted into higher rank. Right, so now we have special coordinate systems. We have more of them, so they're labeled by, again, ideal triangulations, plus some additional data, and that additional data is a choice of reduced word for the longest element in the while loop. Okay, for instance, if you have PGL3, then there's only two, so the while group is a symmetric group on 3 letters, and there's only two possible reduced expressions. For the long word, we can write it as first simple reflection times second times first again, or the sort of other side of the third relation, which is 2 s 1 s 2. Okay, so on surface, which we had to erase before, we have two special charts. Parentheses of a single triangle, the only data is the choice of our spelling of W naught. Okay, and how do we go from our spelling of W naught to an element in the group? Well, basically, for each node of the Dinkin diagram, for each simple reflection, we have the corresponding SL2 triple inside of our group key. Okay, and what we're just going to do is we're going to embed our E into G by the SL2 triple. And with our H, we're going to do something slightly different. We're going to embed it as the fundamental co-weight corresponding to so for SL3, the H will be like an H1 of X, which is X, X1, and an H2. Oh, sorry, I guess it's H2, right? Vanishes on the first simple root, and H2 of X vanishes on the second, so it's going to be X11.
Second one was which one?
Second one is the yeah, H1, because it conjugates, it acts trivially on the second. Okay, so what our spelling of the longest element in the while group does is tells us in what order we should be modifying together these kind of elementary pieces, right? So the fact we have S1, S2, S1, but first we have an H1, then an H2, and then an H1. On the other hand, we could have an H2, E2, H1, E1, and then another H2. So I won't say anything more about that really, but that's sort of the flavor of how it goes. Okay, right. I want to make
So, like in this, so H would be a product of three and choose two things basically, like in this formula. Okay.
So like so what you have is sort of what gets associated to
the red.
To the red, yeah. So to the blue is now a product of roughly n choose two things involving H's and E's.
Yeah.
Yeah. That's right. Okay. Good. So the other really important thing that these toric coordinates do, other than being a nice coordinate system exhibiting the sense of vacuum variety, is to kind of encode combinatorially the Goldman slash what Poisson structure on this frame modulus. So in the case of the classical character varieties, this is nice Poisson structure, which has appeared a couple of times already in the scope. And you can define a similar Poisson structure for these framed guys. And the sense in which these toric coordinates encode, I say encode this Poisson structure, is we can ask what the bracket of any two toric coordinates is, so the eighth one or the kth one. And the sort of miracle is that this bracket is just proportional to their product with some integer coefficient epsilon j. Right, so this Poisson bracket is encoded by some integral skew matrix. Okay. Right. And you can read this off sort of from the adjacency matrix to some auxiliary graph in the triangulation that I won't inflict.
And this doesn't depend on the type?
Absolutely, yeah. So from the data of your triangulation and spelling, you'll be able to draw some kind of auxiliary graph, and the adjacency of the auxiliary graph will tell you the so. Okay. All right. So in the little bit of time that I have left, I want to explain where the quantum topology comes in. And what it does is that this really simple form of the Goldman bracket in these coordinates lets us sort of do a canonical quantization of these modulus spaces. So what kind of quantization do I want to think about? So I want to think not of a sort of formal quantization, but of a sort of honest sort of quantization, where we're going to take a quantization parameter h bar to be some real number, positive real number, let's say, and we're going to have a sort of auxiliary quantization parameter q, which is going to live on the unit circle, and I'm going to parameterize in a sort of funny way as e to the pi I times the square of my. So what's the idea of the quantization? Well, we want to promote the toric coordinates to generators of a some other algebra which came up in the school, quantum torus. So now we're going to have let's call these capital X's to sort of disambiguate. So we're going to have capital X1 through capital XT. We're going to satisfy skew commutativity relations where the degree of skew commutativity is q raised to twice the, I guess when we do it this way, q raised to twice the power of this epsilon. All right. So this it's sort of often useful to think about this quantum torus and the effect of representation theory in terms of a Heisenberg algebra. So it's an honest Lie algebra with generators. We call these. Sorry for so many x's. A little x1 through little xt is just honest, now honest lead bracket with xk is equal to 1 over I times this epsilon. Right, and then we can embed this quantum torus into the completion of this Heisenberg algebra by saying the k fund of the big x's is either the 2 pi h bar times the corresponding little x. Right, and the point of doing this is that this Heisenberg algebra has some nice field space representations. Element of linear function on the kernel of my epsilon matrix. Right, so let me just as an example, let's take the simplest possible thing where our epsilon matrix is non-degenerate and just 2 by 2, right? So we just have a single pair of little x's, x1 and x2. Well, in this case, by the Stern-von Neumann theorem, this Heisenberg algebra has a unique representation of Poisson-Morphism, which you can model as integrable square integral functions in the line. And the generators are represented by the usual kind of momentum and position operators in quantum mechanics, right? So, operator of 1 over 2 pi adjunct derivative, operator of multiplication by the coordinate on the line. Okay. All right. So these guys are a simple joint, unbounded, but a simple joint, and so they're exponentials because our quantization parameter is positive real, or just real at all. These guys here are positive operators. And unbounded, but positive operators in the space. So you could think of this sort of class of representations as being some quantum version of this totally positive locus in the character domain. Sort of a class of representations where the cluster coordinates are acting like positive operators. All right. So what becomes of the gluing data? Right, how do we glue these two charts together? What's the analog of these subtraction-free bidirectional transformations? We promote these subtraction-free bidirectional transformations to unitary equivalences of the Hilbert space to itself. And what are these unitaries? Well, for each one of our cluster coordinates, for each direction k, we have a unitary transformation that I'll also schematically write as phi of x of k. All right. And now the sort of crucial theorem is the following, right? Which is that if we're in this case where we have p and x, this commutator is 1 over 2 pi I, then the corresponding unitaries phi p, phi of x satisfy what's called the pentagon identity. So this composite phi p, phi of x is equal to the composite phi of x, phi of p plus x, phi of p. Okay, this is the pentagon identity. All right, so the great thing about this pentagon identity is it allows us to get a representation of the mapping cluster to the surface on our Hilbert space. So let me finish quickly by explaining that. Right, so remember the mapping class group of the surface is the group of diffeomorphisms of surface molecular isotopy, those isotopy of identity. And we're going to construct an action of the mapping class group in the following way. So we're going to introduce a kind of combinatorial space. We call it P for Ptolemy, right? And this space is going to have vertices given by triangulation, ideal triangulations, mod consider after isotopy. I'm going to put an edge between two triangulations. If, like these fellows over here, I can go between them by performing a flip. Okay, and I'm going to put faces of two kinds. I'm going to put some sort of trivial kind of faces. I'm going to have square faces for any pair of edges E1, E2, not in the same triangle. Right, so I can start off with a triangulation. I can flip E1, or I could flip E2, and then I could flip E2, and then I could flip E1. I'm just going to go to final, whatever. And I want to put a face in my complex whenever I have this kind of square with two edges and not the same triangle. So it's a kind of boring face that I want to put. But the interesting one is these pentagonal faces, which correspond to edges that are shared in the same triangle. And I've drawn a picture of this pentagonal face on this top right-hand board, right? So the point is that given a picture like this, where we have a pentagon, there's two equivalent ways I can pass from this initial triangulation T0 to the final one T1. I can first flip A, and then B, and then A again, or I can first flip B and then flip A. You see I come back to the same final triangulation. I'm going to put a face in our complex, also for these pentagons. Right, and the great thing about this Ptolemaic complex is that it's connected. So you can get between any two ideal triangulations by doing enough flips, and once we've thrown in these faces, it's simply connected as well. Right, so up to pentagons and square moves, there's a sort of unique path in the space of flips. Right, so the upshot is, okay, well certainly if we have two elementary transformations corresponding to edges not in the same triangle, the corresponding unitaries commute. So we have this square being filled. And also, by this pentagon identity, we have this pentagon being filled. All right? So the upshot is that we get a representation of the mapping class group of a surface on this. Okay, so how badly out of time am I actually playing?
4 minutes?
4
minutes past time.
Oh, so I should, yeah, probably so.
Questions?
The very beginning it said G has to be sigma.
Yeah. I suppose, I mean, you could do it, I think, probably equally well for semi-simple or product of simples, except kind of the combinatorics involved in showing that you have this pentagon relation involved will be somewhat more complicated. But I'd probably easy to figure out. I don't think it's a serious issue.
As lambda varies, these representations are all essentially the same.
No, they're not. Yeah. Yeah. I mean, it's sort of like the same thing. It's like sort of specifying a central character.
Yeah.
Yeah. I mean, it's Hilbert spaces. So it's like a sort of flat family of Hilbert spaces, but as representations of the algebra, they're different. The center of the algebra is acting by different.
No, but for the Heisenberg,
Oh!
they all look essentially the same. But when you go to the mapping class group, they might change depending on the level.
Why is this here for the Heisenberg? The different center of characters is
Like the point is that we allow this epsilon matrix in general to have a kernel, so that you can allow the center of the Heisenberg algebra to act by different. Oh, okay.
Still,
Oh, you mean?
I mean, I have this picture of a big line in a plane.
Yeah.
And all along the line, they all look more or less the same, even though they have different central characters.
Right. Like as Hilbert spaces, they're all the same. Yeah. Oh, you mean? Now sorry. I think I thought you understand the question. Are they equivalent as representations of the mapping class group?
Yeah.
Yeah. I think it depends on if you want to talk about pure mapping class group or like the one where you have mapping class group relative to the functors or not. As representations of the pure mapping class, so of the one where you are allowed to twist the functors, they're equivalent, but not if you don't allow to twist the functors. Yeah.
I think I got lost. But it seemed like this H is a representation of the quantum torus.
Yeah, that's right. Mm-hmm.
So how does that turn into a representation of the mapping class?
Right. So the point is that what we're doing is we're saying the mapping class group acts on the set of all of these ideal triangulations up to isotopy. And what we're going to do is we're going to say that we to describe how a mapping class group element acts, we pick our favorite triangulation, do this mapping class group element, get a new triangulation, which is related to the old one by some big sequence of flips. And now we know, for each one of the elementary transformations that makes up this big sequence of flips, we've associated some unitary operator on the Hilbert space. This phi of the corresponding variable that I sort of swept under the rug a little bit. And to get the axiom of the mapping class group element, you just multiply together all of these phi's for all the flips that you did. And then because of this magical pentagon relation, that doesn't depend on what sort of order you chose to flip things in.
So an edge in a triangulation gives you an operator, and it also gives you a flip.
That's right.
Which gives you a path through different triangulations.
Yeah, that's right. Yeah.
Does this Python relation has to do with anything with like Python relation for quantum algorithm?
Yes. So this function phi is the quantum algorithm. That I swept under the rug as well most of the time. So this phi is the unique solution of the pair of difference equations when you shift the emerging through direction by one step of quantization parameter, you get 1 plus Q inverse into the 2 pi quantization parameter Z by XZ. So and so there's two of them. You should get a shift by the quantization parameter H bar or its inverse. Okay, so this pair, provided H bar is irrational, has a unique solution, and that solution is quantum developed. The representation of the mapping class group?
Yeah.
That is an excellent question. Sasha, do you know if the mapping class group representation is faithful?
I guess you need to take sort of for to SLN as n goes to infinity.
Yeah.
For fixed SL2, it
Right.
would surprise me that if you consider the question for all n.
Yeah, that's a good question.
No, I think that's a bit of an equal to
Although,
yeah, I think it could. I would imagine. Like, I kind of come up with a point.
I think the like 10 minutes over time. So I think we should like thank Gus again.